All right, we're going to continue on here. Chapter 4 seems good. So we've been talking about really electron configuration last time. And remember that electron configuration basically gives the order at which electrons go into the atom. Remember that electrons again go into these orbitals, which are these sort of areas within the atom that molecules basically sort of house. Remember that they are basically sort of electron density type maps, basically probability type maps. There are a few different types of atomic orbitals that we talked about, which are S, P, D, and F. Remember that any individual orbital can only hold a maximum of 2 electrons. And since there's only, in terms of how many are types, there's one s orbital, there are 3 individual p orbitals, which again make up a subshell or sublevel. There are 5 individual d orbitals that make up a d subshell. And there are 7 different f orbitals that make up the f subshell. That means that the maximum electrons, if you sort of fill all these guys, would be 2 for the s. If you filled up all 3 of the p orbitals on any energy level, which is a subshell, that would be 6. 2 times 5 would be 10 if you filled up all the individual d orbitals, and 2 times 7 is 14. Remember that also really important in terms of these orbitals is really the energy level at which it actually starts. So remember on the first energy level, which is the n equals 1, that's the lowest in energy, that is the closest to the nucleus. There's really only s orbitals there. Basically, that's the only type of orbital is present. And remember that you can kind of make a little chart to help you figure out the order by remembering that. We also should remember that it's not until we get to the second energy level, or n equals 2, that we first start to see p orbitals appear. And again, like I said, you could kind of just go down to the right of it and put 2p. Again, it's not until you get to the third energy level that is the first appearance of d orbitals. Once again, you can kind of step it down there and move it over. And lastly, the fourth energy level, or n equals 4, is where we first start to see f orbitals. And again, the reason this is important to sort of go diagonally down is you can recreate for yourself really easily at this point the order at which electrons go into the atom by frankly just going the numbers in order and putting the same letters. So right underneath here would be a 2s, a 3s, a 4s, a 5s, a 6s, and a 7s. Basically, there's 7 energy levels, so we go up to 7 basically. And then you follow that for the P as well. 2P underneath would be 3P, 4P, 5P, 6P, 7P. And then under the D's, 4D, 5D, 6D, and 4F, 5F. Again, if you put honestly, like I think I might have mentioned yesterday, put a couple extra numbers in that area, you'll probably still be okay because you're probably never going to get there too many times. So even if you kind of went a little further than you should have, you would be okay. This is the correct order in which electrons go into the atom. And as you can see, it took me less than 30 seconds probably to make this. And again, if you just understand how to make it, then you will actually have, obviously, the order. We always start up on top and we basically follow arrows. If we're done with an arrow, we then kind of zigzag back and we keep kind of following that pattern. And the important part is, as we talked about after the 3P, remember that the S's come before the D's, and then we have that pattern again continuing on. And obviously, you can keep putting your arrows in there. But again, we always have sort of the S's before the D's, as we have 5S here before 4D, just like we had 4S before 3D, and so forth. So you can just kind of continue your sort of pattern down. So this will allow you really to write any electron configuration that you need. So as we talked about as well, we did a number of examples. I think if we were going to write the electron configuration for something, just say We'll do Mn, which is 25. So Mn is atomic number 25, which means it does have 25 protons. And obviously, if it is neutral, it would also have 25 electrons. So if you're writing electron configuration for anything that is really neutral, and also a reminder that things really do not get charges unless they start hooking up with each other, really a metal and a non-metal. So if you really just have like an element by itself, it has really no charge. We would follow our starting point here, and we would write something like 1s2, 2s2, 2p6. Once again, if we count up our top numbers, this is how many electrons we basically distributed into those orbitals. So that's 10. We got to keep going. Obviously, after 2p, that takes us to 3s2, then to 3p6. Remember, at that point, we're right about here. We are going to go to the 4s next. So remember that 4s squeezes in there and actually does come first. Before we then head into basically our 3D in this case. And up until this point, we got 2, 4, 10, 12, 18, 20. So obviously here, since D could hold 10, that would be a 3D5 situation that's occurring, I guess. Yeah. Question on the electron configuration there. We also talked about, I think, a shorthand that you can do, and the shorthand is usually using a noble gas that comes right before the element that you're writing on the periodic table. In the case of Mn, our noble gas would actually be up through this part. And if we count up our numbers up on top, that is 18. And number 18 on the periodic table is argon, which is a noble gas in group 8. I think we also talked about the periodic table as well yesterday. And again, we would continue on with the electron configuration as well. Question on that there. Yeah. How do you know when to stop? When you put in all the electrons that it has. So in a case of like this guy here, we know for sure when we go to the periodic table, we can find its atomic number, right? And its atomic number is really the definition of how many protons it has, right? So if this is a neutral atom, which most of the time it probably will be in a lot of cases, unless it's an ion, but in this case, it does not have any charge. So we don't see anything written there, so we know it has basically no charge. So what that means, in order for it to be neutral, it has to have the exact same number of electrons, which means it has to have 25. And basically, we always start up here, and we basically just keep distributing those electrons until basically we've, in this case, put in there 25. And that's where we should stop. The bracket is a shorthand for the long configuration, and it's sometimes referred to as the noble gas configuration, which means it has to always be a noble gas, which is, again, thank you very much, which is on the periodic table, group number 8. Yeah. So if you look on the periodic table in group number 8, what you will see is argon. And then if you continue on into the next row or period, right about halfway through there, you'll find Mn. So if you back up from Mn, the first noble gas that comes, right before it is out. Yeah. So it always has to be, when you do this, the noble gas that comes before it, because when you're writing the electron configuration, you got to stop, in this case, like at 25, right? Which means you can't go to the one past it because that's too many electrons, right? So the shorthand is taking out basically the electron configuration for the noble gas part of it, and then you just kind of continue on until you again get to the number that you need. Yeah, so yep. Other questions? Now, again, we also talked about the idea of valence electrons, right? And valence electrons are the highest energy electrons. Now, transition metals are a little bit different than most representative elements. If you look on a periodic table, perhaps, or you count the groups starting with group 1, and you get to where Mn is, not drawn to scale, it's actually higher up there. it will be a number 7 basically group, and that is how many valence electrons it has, because available to this guy is basically all those guys are available to be its sort of valence electrons. Now, the number of valence electrons, which is the outermost electrons, again, if we looked at something like magnesium, which is 12, once again, it would be 1s2, 2s2, 2p6, 3s2. We also can shorten this guy up if you wanted to. That is 10. And again, if you look on the periodic table, that is neon's configuration, 3s2. Again, neon coming right before magnesium, and that is the noble gas that comes right before it. So that is sort of how you shorten up the shorthand of it. It has 2 valence electrons, which are these guys here, which is the outermost electrons. And again, it is equal to the group number of valence electrons. So magnesium is group number 2. It has 2 valence electrons. When we deal with the transition metals, again, it's just sort of the straight numbers. 1 through 18 is kind of what you use to number all the groups, and whatever group that transition metal is in, it would be how many they have. Any questions on electron configuration there? So a couple other things that we also talked about was that you could, if you sort of know what you're doing or sort of understand what you're doing, you can sort of count off electron configuration from the periodic table. So when we look at group 1 and 2, that is our S block, and it basically has 2 electrons, 2 groups. If we look through group 3 through 8, that is 6 groups, 1, 2, 3, 4, 5, 6, and each of those boxes would represent 1 p electron. The D block here is really our transition metals, and there are 10 boxes if you count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, each one represents basically a D electron. And on the bottom is our F block, and I won't count them all, but there are 14 boxes down there, and each one goes there. You could use the period numbers, the ones that go 1, 2, 3, 4, 5, 6, 7, and 8 as sort of the energy levels, basically. Remember, I think as we talked about at the very end, you do have to be careful because I guess I wrote it pretty good there. When you get through here, which is technically 4s1, 4s2, remember that the D actually starts on the 3rd energy level. So right there is 3D, even though it's on the 4th period, it is 1 less than that. And then it also gets a little crowded and crazy down in here. That's 4F and 5F, those 2 rows, which once again basically go, over in this area. And they're actually a couple behind the actual period number. So I would recommend that if you're going to sort of count it off the periodic table, you can definitely do it. You probably will be fairly safe on anything on the outsides, as long as you remember kind of the D part of it there. But again, there's a lot of craziness, especially if you get deep into here where you got to kind of incorporate those guys in. So it's probably best to follow the chart like we had up there. But you definitely could do that. So for example, the one we just did was MN, which would be right about there. And again, we would go with our 1s2, that would take us to helium. Our 2s2 would take us to beryllium. Our 2p6 there would take us to neon. Our 3s2 would take us to magnesium. Our 3p6 there would take us to argon. Again, our 4s2, and at this point, as long as you remember that is 3D, all you have to do is count the boxes: 1 box, 2 box, 3 box, 4 box, 5, 6, and 7 there. Except I put them in the wrong box. Maybe one more over there. Number 6 would be much better there for in the land. So again, you can just really count it off as long as you put your element in the right box, I suppose, right? That shouldn't be a problem. The periodic table will be printed for you. Any questions on the periodic table electron configuration? All right, so again, here's another example of that sort of shorthand. That is potassium. Again, that is for argon sort of core. And again, you just kind of continue on. So let's talk a little bit about sort of what happens for example, if something does sort of gain a charge and what happens with the electron configuration for things that are ions. And we've talked about ions a little bit as we've been going through. And again, a reminder that ions, there's basically a cation, which is positively charged, and there are anions, which are negatively charged. Remember that this basically is somebody that has lost an electron and somebody that has gained some electrons, which is why they become negative or positive. So if we take something like magnesium that we just wrote the electron configuration for, which is 12 when it has no charge, again, 1s2, 2s2, 2p6, 3s2 in this case. Now, when magnesium does gain a charge, it will always become a +2 charge. So that means that it has lost 2 electrons. And that means that it will have how many electrons? Something with a +2 charge here then would have 10 electrons, right? 10 negatives, 12 positives, leaves you a +2 over. I think we did that when we were doing protons, electrons, neutrons, atomic number. So you do have to adjust the electron configuration. So the electron configuration for magnesium with a +2 charge, 1s2, 2s2, 2p6, that would be. That is how many electrons? That is 10. And on periodic table, number 10 is neons. Yeah. So that is the same electron configuration as neon in this case. Yeah. Now, if we look at something, say, like our friend oxygen. Oxygen with no charge is, I'll get the right number up there, 8. 1s2, 2s2, 2p4. Oxygen, when it forms a charge, is a -2 charge, which again means that it has now gained electrons. And the 2 is how many it gained. So instead of 8 electrons, this guy's going to also have 10, which means the electron configuration for for oxygen with a -2 charge, or oxide, 1s2, 2s2, 2p6, also still neon's configuration. So all three of those things, magnesium with a +2 charge, oxide, which is oxygen with a -2 charge, and neon, they are all what are known as being isoelectronic with each other. That is a fancy way of saying they have the same electron configuration. So they have basically the same electron configuration. But what is actually happening here is actually really important for the next chapter we're going to talk about, which is bonding. What's really, really happening here is if you look at sort of the positions of everybody here on the periodic table, we have magnesium about here, got oxygen right about there, and we got neon right about there. When magnesium loses electrons, it basically backs up to the same electron configuration as the noble gas that came right before it. And when oxygen actually gains the electrons, it finds itself moving forward on the periodic table to the noble gas that comes right after it. That's really important because noble gases are chemically inert. They are super stable, as we'll talk about many times probably in the next chapter, which is the bonding chapter. That is really the whole purpose of bonding, is for everybody to end up like the noble gases in terms of their electrons, which is a really, really stable situation. So representative elements, which are pretty much your elements that are not transition metals. So kind of to the left and right there of transition metals. So all those guys not drawn to scale here. This is our transition metal region. All those elements kind of to the left and to the right in groups 1, 2, 3, 4, 5, 6, 7. That is the way they become really stable, is through bonding. And through bonding, they're able to achieve the same electron configuration as a noble gas. Metals typically will lose electrons and back up to the noble gas that came before them. Non-metals will typically gain those electrons and go forward in terms of the noble gas that comes after them. So if I had, say, something like sulfur with a -2 charge and say calcium with a +2 charge, right? The electron configuration for both of those. You look at sulfur on the periodic table, 16. Calcium is 20. Okay, so let's take a look and see. So starting with sulfur, in a neutral sulfur, it has 16 protons, which also means it should have 16 electrons. In this case, our sulfur, which is sulfide, has a -2 charge. Again, the minus means that it has gained electrons, and 2 is how many it gained. So our neutral guy has 16 electrons based on the atomic number, which is the protons. That means that this guy should have 18 electrons, right? So a little 1s2, 2s2, 2p6, 3s2, 3p6. That is also our good friend argon's configuration, right? And that it would be the noble gas configuration. Again, by gaining 2 electrons here, it's able to achieve that noble gas configuration. Calcium has 20 in a neutral situation protons, which means it also has 20 in a neutral situation of electrons. The +2 means it has lost 2 electrons, which means it also will end up at 18 in this case, right? Which means he has the identical electron configuration, our argon's configuration. Once again, if you look at the location of these guys on the periodic table, you got kind of this situation happening. Calcium backs up to the noble gas comes before it, and sulfur goes forward to do it. Again, they both achieve noble gas configuration. Do they become argon, both of these things? Are they now argon? The answer is they are not argon. Yeah. Because when we talked about protons, electrons, and neutrons, which particle was the most important in terms of which element it is? Protons. So the only thing we changed here is electrons. So sometimes people have a misconception about that they become those elements. They do not. They are still, for example, sulfur and calcium, because they still have the correct number of protons. But now they have an electron configuration that matches up to what is found in a noble gas, and that's the part that makes them the same as the noble gas, and it makes them more stable that way. But they're still those same elements because we didn't do anything with the protons in this case, obviously. Otherwise, it would change elements. Question on that there. So we talked about transition metals, and we did talk about, I think, as well, in terms of transition metals, that there are a couple of exceptions to the normal electron configuration. And the two that you're responsible for, again, is chromium, which is 24, and copper, which is, I was going to say 25, it didn't seem right. 29 seems good. And when the electrons go into a transition metal, because of the order there, which is the 4s comes first, and then the 3d comes next in terms of energy. Once again, they will fill the 4s and then start filling the 3d afterwards. It has been found experimentally that something like chromium actually is more stable in a configuration where one of the s electrons have been sort of promoted up to the d orbitals, and they could do that because they're super close in energy to just begin with. So we actually end up with a configuration that looks something like this, and that is the difference there. Again, if you were going to follow the kind of zigzag thing that we've been using, you would end up with like 4s2, 3d4 at the end of it. Again, just experimentally, it's been found to have this configuration. That again is also argon if we shorten it down, 4s1, 3d5. That essentially puts an electron into each of the d orbitals, also puts an electron there in the s orbital. And one of the things we don't get too much into here, which is something known as Hund's rule, which is things tend to be stable when you maximize electrons all kind of going in the same direction. And what that does is it maximizes sort of all those electrons heading in the same direction. Copper is a super similar sort of exception. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, once again, only one electron in the s, and 3d10, rather than what you would normally get if you just follow the zigzag thing, which is 4s2, 3d9. So again, one of those electrons from the s goes upwards, and that is the difference there. Also, you could shorthand it if you want, argon 4s1, 3d10. When you look at the periodic table where chromium and copper are, and again go down and kind of in, there's a ton of sort of exceptions to electron configuration, but for our class, you'd just be responsible for chromium and copper. Everybody else you could just write using the little chart thing that we made and put in order. Just know in real life, if you wrote something for like silver or PD, it won't be correct because they have electrons in different places. Like PD has actually no electrons, which I might have mentioned last time. In the S, they've all been sort of upwards to the d orbitals. Now, another sort of weird thing that happens with transition metals and what happens when they actually do form charges is there is a little bit difference in terms of how they kind of do charges. So when we think about metals, they will typically become positively charged. And if we think about sort of our metal examples there where we just did, our guy here will lose really those last electrons that were there. And again, our magnesium lost those last electrons in the electron configuration. But transition metals are a little bit different in terms of what happens when they do gain charges. So we'll take a look at iron, for example. If we look at iron with no charge, that is 26. So again, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Once again, if you want to shorten it down, right about to there, argon, 4s2, 3d6. So if we look at the electrons here in iron as they sort of go into iron, basically, as they're being filled, if we just look at the last electrons, which is our 4s and our 3d, what's going to happen is it's going to fill here, and then it will put in its 6 electrons, which will look something like this. Again, actually one at a time, and then come back and pair up. Now, what happens with transition metals, which is a little bit different than what happens with representative metals like in group 1 and group 2, is once you start actually filling the d orbitals, these two sets of orbitals basically will switch energy. So they'll actually switch sort of positions and energy. And what ends up happening is the 4s actually becomes higher in energy than the 3d. Now, this is really important in terms of when a transition metal loses electrons as to what electrons it will actually lose first. So elements in general, when they lose electrons, which are basically metals, they typically will lose the highest energy electrons first, which are like those valence electrons. So in the case here of iron, because there's the switch that occurs, when iron, for example, becomes a positively 2 charged, it will not have 26 electrons. It will have how many? 24 electrons, right? And that means that it will need to lose 2 electrons from its configuration. In this case, which orbitals are actually the highest electrons? It's actually these guys, because of that switch that occurs. And it will actually lose first because of that switch that occurs. In this case, that s orbital is holding how many electrons? 2, right? And that's exactly what we need to lose. So those will get lost first, and the correct configuration here would be, if you just kind of shorthanded it, argon 3d6, with these electrons being lost first, basically. And that happens with, I'm pointing over there because I felt like the periodic table should be there, but it's not, so I'll point over there. That happens with all the transition metals. They will always lose those s electrons first. And then what is different than sort of representative metals is if they need to lose more electrons, they could do that, because in addition to the 4s electrons, it also has all these that can be considered valence electrons as well. So it has a little bit more electrons that they could kind of lose if they need to make a variety of charges. And that's why, as you might know, and as we'll talk about in the next chapter, transition metals have the ability to make multiple types of charges because they have the ability to do that. They got plenty of electrons to kind of make different charges. So the other difference is, did my iron with a +2 charge get back to noble gas configuration? Is it at the same electron configuration as a noble gas? It is not, right? It still has 3d6, right? It has, at this point, 24 electrons. It doesn't have 18. I'm sorry, yeah, it doesn't have 18 argon. It doesn't have 36 like krypton. It is stuck there in the middle. So that's also very different for transition metals. Unlike metals in group 1 and 2 and even 3, they will back up to the noble gas in terms of electron configuration. These guys typically will not, because how many electrons total would something like iron has to lose to get all the way back to 18? It would have to lose a grand total of 8 electrons to get back there, which means it would have a +8 charge, which pretty much is not going to ever happen. So they don't typically get all the way back to a noble gas configuration like representative elements do because of that. But what would happen, though, if I actually had iron with a +3 charge? How many electrons would it have? 23. So we already know that we're going to lose these two, right? Again, at this point, the next option is right there, right? We got to take one of them out of these Ds, and that would leave us at argon 3d5, yeah? And that would be electron configuration. So transition metals are definitely different the way they lose electrons in terms of their electron configuration. They don't end up at the noble gas configuration. They have a lot more electrons that they could kind of pull from. And again, if you look on the periodic table where iron is sitting, and if you just counted all the groups above it from the left to the right, that is group 8. And again, that 4s2 3d6 is the 8 technical valence electrons it has. Again, it will never live to lose 8 of them at a time, but it mostly will lose 2 or 3 at a time. So transition metals always dump the S's first because they end up being higher in energy because of that switch that occurs in the energy once you fill the d orbitals. And that's what I was talking about, I think, the other day as well, that sometimes people will write electron configuration based on energy, and that's why it all kind of goes in order, the 3s and the 4s and stuff like that, because there is that switch that occurs. But nobody ever in these type of chemistry classes or any chemistry class really writes them that way. So you should always, again, follow the order here. Any questions on that there? So then why don't you write the electron configuration for your favorite ion? I don't know, which is nickel with a +4 charge. Why not? In case you don't have a periodic table, nickel is hanging out at 28. Okay, so let's take a look. So we'll start with nickel, actually, with no charge, which has 28 electrons. Again, the mass is 28 protons. That would get you a 1s2, a 2s2, a 2p6, 3s2, 3p6, 4s2, and a 3d8, I think. It's 3d8, if I'm mistaken, I think, in that case. Now, still a little bit of this here. We'll go 8 and 8 there. And that means that basically we got 1, 2, 3, 4, 5, 6, 7, and 8 electrons, right? It's going to end up there. Now, with a +4 charge, that means it's going to end up with 20. 4 electrons, right? So again, here it's going to lose its S1s first, and that is 2 electrons that were in there. We then need to come into here and actually take out 2 more electrons for the 4 total that we need to remove, right? So 2 from the S, that gets it to a +2 charge, and then 2 more from the D, which would be the next highest. So we basically be taking these electrons and like these electrons out. And that will get us basically here 1s2, 2s2, 2p6, 3s2, 3p6, 3d6 are argon 3d6. By the way, same electron configuration as this guy, yeah, as well. They are also isoelectronic with each other. They have the same electron configuration. Question on transition metals and if they have a charge. So again, slightly different. It's not the last electrons that are written for transition metal. It's always the S's first, and then, if necessary, into the D's. The good news about things in group 1 and 2, and really 3, which is aluminum, is pretty much the last ones written is the ones that you take for those guys. But these guys are a little bit different. Yeah. Say it one more time. Sorry, say it again.
How you did it? I didn't add the first 2. I just straight ahead the 1 is 2, 2, 6, 3, 2, 6, and 2, 6.
Yeah, that would be perfectly fine if you were doing this one. Yeah. I just wrote this one just so everybody could visualize to see which electrons are being lost. Yeah. And the one I wrote first was actually for nickel with no charge, basically. Yeah. Other questions? Okay. All right. So that's fun electron configuration stuff, I suppose. All right. So we're going to talk about now to kind of finish up this chapter some periodic trends. And we also talked about the periodic table. So we've talked about this, I think, as we were going through it. But again, officially, valence electrons are the outermost electrons. They're the ones in the highest energy level. They are really important, as we'll see in the next chapter. They're pretty much the ones involved in bonding. And that's because if you just visualize it, they're on the outside, furthest away from the nucleus. So when 2 atoms come together, they're like the first electrons that will say hello to each other. And they're also further away from the nucleus, which means they're not going to be held as tightly. So they're able to be kind of removed or shared in that sense. You can find the valence electrons again by writing the electron configuration like we have nitrogen here. Remember that that's the first energy level. There's 2 electrons on the second. 2 and 3 is 5. And once again, though, nitrogen is group number 5 on the periodic table, and it will have 5 valence electrons. So that's definitely the much easier move, as we talked about, to figure out valence electrons is simply to go to the group number, and it will tell you how many valence electrons it has. Again, as I just mentioned a second ago, and as we just looked at, if you're dealing with the transition metals, again, just count like 1 through 18 numbering for all the groups, and those numbers will give you the valence electrons for transition metals, which are basically between 3 and 12, basically, in the transition metal region. So fluorine's group 7, has 7 valence electrons, so is chlorine. Carbon is group 4, and it has 4 valence electrons. Again, if we looked at carbon's electron configuration, 1s2, 2s2, 2p2. These are the highest energy level. 2 and 2 is 4 for its valence electrons. And again, that is the valence electrons. Now, when we talk about metals and nonmetals and sort of reactivity that occurs, what we tend to see based on what we're going to talk about here in a second, which are some periodic trends, is as you go down a group for metals, they typically will give away their electrons a lot easier, which means they are actually a lot more reactive as you go down a group on the periodic table. And that's opposite for sort of the nonmetals. Nonmetals kind of get more reactive as you go up a group. And when you look at the periodic table, upper right is the most reactive nonmetal. Remember, nonmetals are up and to the right. And lower left is the most reactive metal. And the reason that is a lot of these periodic trends that we're going to talk about. And this will also help explain, again, why we see, for example, metals typically will give away their electrons and why nonmetals will typically want to gain electrons and accept electrons. So let's talk about some of these trends here and see how they all sort of relate together. The first sort of trend we're going to talk about is what is referred to as ionization energy. Ionization energy is the energy that's required to remove an electron in the gas phase of an atom. So when somebody loses an electron, you typically will see the electron on the product side, like it's being given off. And as you can see here, when it loses that electron, it becomes positively charged, as we know. And the ionization energy is that energy required to remove an electron. So if you have high ionization energy, does that mean it is easy or harder to remove an electron? So if ionization energy is the energy required to remove an electron and you have really high ionization energy, would it be easy or hard to remove your electron? It actually would be really hard to remove your electron, right? So you would have to put a lot of energy in there to pull off the electron, right? So that's the definition. Ionization energy is the energy needed to remove the electron. So if you have a really high amount of ionization energy, that means you got to throw a ton of energy in there to rip the electron off. The opposite is true if you have low ionization energy. It is, I won't say super easy, but it's easier to rip off an electron. It doesn't take as much energy to convince somebody to part with their electron, basically. So it's harder when you have that. So metals, for the most part, have very low ionization energy, and nonmetals have very high ionization energy. And that pretty much means that metals are like, go ahead, take my electron. It's all good. You don't need a lot of energy to do that. Nonmetals, on the other hand, are good luck trying to remove my electron. You need to come with a lot of energy to try to rip my electron away from me. And again, that's why it doesn't typically happen in that case. So if you look on the periodic table, ionization energy increases as you go up and to the right and decreases as you go down. So basically increases this way and decreases that way, the ionization energy. By the way, when things lose electrons, they actually come off one at a time. They don't just all drop off. It actually happens in like a stepwise fashion. So for example, if you took something like magnesium that we've been talking about, right? Magnesium, the first thing that would happen is magnesium would lose one electron. That is what is known as the first ionization energy. The first ionization energy is the energy needed to remove just that one little electron, take it off. By the way, let me write this configuration one more time. 1s2, 2s2, 2p6, 3s2. The next thing that will happen is that magnesium that has lost one electron will then lose a second electron. And that is what is known as the second ionization energy. Then maybe what will happen is magnesium that has a +2 charge will then lose one more electron. And that'll be what is known as the third ionization energy. So every electron comes off basically one at a time. There's actually a certain amount of energy required just to pop off, like the first electron, the second electron, the third electron. By the way, let's talk about what happens when somebody loses an electron. Is it easier to remove the first electron or the second electron? Which one should be easier? It is actually much easier to remove the first electron. And that is because when I lose the first electron, let's just say this is the size of the atom, right? And I lose one electron. Does my size of my atom, which is now an ion, would it get larger or smaller? It lost an electron, which means it lost some of that electron density. It's going to shrink, right? And what that does is it brings all the other electrons now closer to the nucleus, right? Nucleus is positively charged, electrons are negatively charged. So now they're really close to each other, gonna make it a little bit more difficult to try to rip off the second electron, right? If I rip off the second electron, what's gonna happen? Gonna shrink even more, right? Now everybody's moved closer to that positive charge of the nucleus, which means it's going to be held even tighter, even harder to remove the third one, fourth one, fifth one, however many you're drawing, try to rip off in this case. So as you go, for example, from the first ionization energy to the second to the third, the ionization energy increases. It gets much, much harder, much more energy to do. So maybe it's like 700 kilojoules to remove the first one. Maybe it jumps up to like 1400 for the second. And maybe it jumps up to like 7,000 kilojoules to try to remove like the third electron. Yeah. Now, when we look at the electron configuration, right, for magnesium, it has how many valence electrons? It has 2, right, which are these, right? That's its valence electrons. The lower energy ones, which are closer to that positive nucleus, are called core electrons, right? The reason why the ionization energy jumps so much as you go from the second to the third electron in the case of magnesium is after you lose 2, what type of electrons you left with? You're left with core electrons. Good luck trying to rip those things off because they started close to the nucleus and now they're even closer to the nucleus because they lost some more electrons. Not going to happen in terms of energy. And that is why something like magnesium will pretty much not do that because it's not energy efficient to rip off a core electron. So the best it could do is just drop its 2 valence electrons. And that's why something like magnesium always has a +2 charge, never a +1 charge, never a +3 charge. It will always lose those 2 valence electrons and won't go any further because the energy won't allow it really to lose one more electron. Question on that there. So again, when we talk about a neutral atom and something that's a cation, it does get smaller. And again, that's going to bring all those outer electrons closer. So in general, the first ionization energy increases as you go up to the right, decreases as you go down. And for every electron you try to rip off, it gets harder and harder to do that because, again, they're getting closer and closer to that positive nucleus and going to now be held a lot tighter. Now, some other important sort of trends, for example, is one known as electron affinity. Electron affinity is the energy change when an atom gains an electron. So we talked about ionization energy, which is really when somebody loses an electron, becomes positively charged or a cation. Electron affinity is kind of talked about in terms of anions being made because they're going to gain electrons. In general, it's not a perfect trend, but in general, it increases as you go up and to the right. It decreases as you go down and to the left. Now, another one that sounds like it, but is actually different is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. Now, when you look at the periodic table, it increases as you go this way, with our friend fluorine being the most electronegative element you could have. And it decreases as you go down. If you look at the periodic table, the only elements to the right of fluorine are the noble gases. The noble gases are chemically inert. They ain't looking to do anything. They actually have no electronegativity. They're like, just leave me alone, I'm good. Everybody else is trying to become like them. And that's why we kind of top out in terms of electronegativity and reactivity, kind of up there to the fluorine upper right part of it. Another sort of important trend in addition to those is what is sometimes referred to as effective nuclear charge and it's sometimes abbreviated Z effective. That's a Z, not a 2. And this increases as you go to the right and up, and decreases as you go down. But what is it? So let's take a look at sort of what it is, and it will help you understand why certain electrons are not necessarily held as tightly as others. We'll just take a very simple example of lithium, right? It has 3 electrons, has a 1s2, 2s1 configuration. How many valence electrons does it have? Yeah, it's group 1, and this is its valence electron. This is its core electrons, closer to the nucleus. Because lithium has an atomic number of 3, it basically means that it has a +3 charge in its nucleus, right? The 3 protons. And I'll draw them. They're not perfectly like this, but we'll pretend. These are like the 1s electrons here. These 2, right? Just hanging out near the nucleus because they're lower in energy. Then we have our valence electron, our 3rd electron there. Now, one of the important things about opposites attract and charges is the strength of the charge increases, and that increases the attractive force. So something with a +3 charge and a -3 charge are going to be stuck together a lot stronger than something that's like a +1 and -1 that comes together. So the larger the sort of positive negative charge, the stronger the attractive force is to it. Now, when we look at these core electrons, which are down here, they are pretty much right in the way, if you will, of feeling that full brunt of the +3 charge. There's nowhere for them to hide. They're basically just going to feel that +3 attraction to the nucleus because they're pretty close to it. So they're just going to be drawn in because of that. Now, when you look at the valence electron, though, this guy, he actually experiences what is known as shielding. And he is shielded from the full brunt of the +3 charge because there is frankly electrons in front of him, if you will. It's kind of like if you went to the movies and you sat down and you had a nice view of the screen. And right before the movie starts, somebody sits right in front of you with a giant cowboy hat, right? Screens out half of the screen. You're shielded, you can't really see it. So that's sort of the idea of what's happening here. So because there's lower energy electrons in front of that valence electron, it doesn't feel that full +3 attraction like those guys do. It actually gets shielded. You could actually calculate it, not that you'll need to, but you could actually calculate it by taking the positive charge in the nucleus minus the number of electrons that are shielding, and these are 2 electrons that are in the way. That gives you a +1. So instead of that valence electron feeling the +3 charge of the nucleus, it's actually only feeling a +1 charge, which means, is it going to be held as tight as those core electrons? It is not. And that is why it's less ionization energy to pluck that one off, because it's just like hanging on. It's not held as tightly. But those guys that are core electrons are much closer to the nucleus, feels the full brunt of that charge, and they're going to be held a lot tighter, which requires a lot more ionization energy to try to remove those. And again, it doesn't typically happen. You can't really pop those guys off. Any questions on that there? So these trends also lead to another important trend, which is atomic size, or sometimes people call it the radius. And as you go from up to the right on the periodic table, it gets smaller or it decreases, and it gets larger as you go left and down. By the way, we didn't talk about it, but when you make a cation, when you make an anion, the negatively charged ion, is it smaller or larger than the neutral atom? If somebody gains electrons, should they end up being larger or smaller? They would be larger because they gain all those electrons in that electron cloud, basically, right? So they get larger, just like when they lose them, they shrink basically down. So when we take all of these trends together, there's a prettier size picture. And as you can see, it gets much smaller as you go up and to the right, larger as you go down. If we take all these together on my made up periodic table here, as we go up and to the right, we have things with high ionization energy. So it increases and it decreases this way. We have electronegativity. Increasing up to the right, decreasing down. We have electron affinity, which again is a different thing. That's the energy change. Increasing up and to the right, decreasing down. We have Z effective, the effective nuclear charge, increasing as you go up and to the right, decreasing as you go down. And lastly, we have size. That's actually decreasing up and to the right and increasing down. So when you look at the periodic table and you look somewhere in this region, upper right of the periodic table, where you have your nonmetals, you have things that have very high ionization energy, which means good luck trying to take away an electron. You have things with very high electronegativity, which means they want to actually take other people's, have very high electron affinity, which means they are able to succeed in that because they're able to gain electrons. They have a very high Z effective, which means even the outer electrons will experience a greater positive charge that brings the outer electrons in, which is why they're also very, very small. So they have all of the trends that basically say, I have electrons, I'm keeping my electrons, and I'm going to take your electrons just for good measure. And that is why what we see with nonmetals is they typically will gain electrons. And when they do make an ion, they will become negatively charged. We have basically, if you go to the left on the periodic table where our metals are, they have all of the opposite trends. They have very low ionization energy, which means if you just look at them wrong, they're going to pop off an electron with not a lot of effort. They have very low electron. Bring low succeed. They have a low effective nuclear charge, which means even the outer electrons will not experience a big positive charge, so they don't come in as far. And that means that the outer electrons are going to be further away from the nucleus. So they have all the trends that make them say, take my electrons, please. I don't care, just take the electrons. It's basically what happens with the metals. And that's why these guys will typically lose electrons and become positive charge are our cations in some cases and our anions on this side. Any questions on those periodic trends, which are really important in terms of bonding as well? That's why what we see happen in bonding. Any questions on that there? Okay. Just to give us a taste of bonding here, Lewis dot symbols, which are sometimes referred to as electron dot symbols, are basically symbols that represent the number of valence electrons in an atom. We basically use the symbol and one dot to represent each of the valence electrons. There is no fast rule, but basically no more than 2 per side, which means there's 4 sides, 2 electrons. That's how many electrons? 2 times 4 is. And who on the periodic table has 8? The noble gases, right? So again, that's a big theme in bonding. So we can figure out the valence electrons like we talked about by looking at the group number. And again, this is an example of what our Lewis dot symbols look like. Lithium has group 1, all has 1 valence electron, 2, 3, 4, 5, 6, 7, 8. The one exception is helium in group 8, and that's because helium only has 2 total electrons. So it can't have 8 valence electrons. So it has only 2 valence electrons because of that. Everybody else in group 8 will have 8. The good news is we really don't do anything with bonding in terms of transition metals, so you don't have to worry too much about those, but we know what the valence electrons would be for those if we needed. Any questions on that there? All right, that is chapter 4. Chapter 6, I believe chapter 5 is nuclear chemistry. We ain't doing that chapter, so it's the only one we're skipping. So off to chapter 6. This, by the way, is also now exam 2 material. Yeah, we just finished exam 1 material. We'll talk about it at the end, but like 7 days from today. Yes, so that is when it's happening. This will be exam two stuff. In this chapter, we're going to talk about a lot of things. We're talking about chemical bonding. We're also going to talk about nomenclature. So this is the chapter we're going to talk about naming and how to name everything. And we're actually going to start with that first, and then we'll come back to the bonding part at the end of the chapter. So here we go, I guess. Yeah. So nomenclature is essentially a fancy word for, I don't know how fancy it is, but for how you name things, basically. So it's basically the names of everything. And really, we're going to talk about two types of sort of compounds that we're going to name. One are ionic compounds, and as we'll talk more about in sort of bonding as well, part of this chapter. This is always when you have a metal and a non-metal coming together. And always what happens in that situation is really because of those periodic trends we just talked about. As we just talked about, metals pretty much have all the trends that make them want to give away their electrons, and nonmetals have all the trends that want to accept those electrons. So if you think about their location as well on the periodic table, they're kind of like opposite sides of the periodic table, right? We got nonmetals upper right, metals to the left. So they have a very big difference in each of those periodic trends. And what always happens because of that is we get this transfer of electrons from the metal to the nonmetal, making our metal become a cation, which is positively charged, and our nonmetal an anion, which is negatively charged. Once again, there is absolutely positively no sharing of electrons here. What holds this together is simply the opposite attraction there, the electrostatic attraction. Opposites attract. That positive charge and that negative charge is basically what just kind of sticks them together and they don't fall apart in that case. And the other type of compounds are covalent compounds. Some people will just call them molecular compounds. And this is always between two nonmetals. And if you think about the location of where nonmetals are on the periodic table, they're all stuck together, upper right of the periodic table, pretty much. What that means in terms of those periodic trends that we just talked about, nonmetals essentially want to bring electrons to themselves. They want to hang on to their electrons, which means when you get two nonmetals together, neither one of them is going to lay up their electrons. Neither one of them is going to give away their electrons. They're both going to go, no, I don't want to do that. And they're going to go, all right, here's what we're going to do. Says, I don't want to give away my electrons. You don't want to give away your electrons. The best that we could do is let's just share them. And that's what happens in that situation is we get some type of sharing that's going to occur of those electrons. And as we'll talk about later in this chapter, it could be unequal sharing or it can be equal sharing of electrons. But in a covalent bond or a covalent compound, there is some aspect of sharing those electrons. And again, it's really because they're both nonmetals and neither one wants to lose their electrons. They both really want to gain electrons. So that's the best that can happen is the sharing aspect. And that's very different than what happens with ionic compounds because like I said before, metals are like, go ahead, take my electrons. I don't really care. And nonmetals will go, thank you very much. I'll take them because I want them. And we get this whole transfer of electron that basically happens. Now, depending on whether you are looking at an ionic compound or you're looking at a covalent compound, the way that you go about naming these things are different. And that's why it's important to be able to recognize what you're dealing with. Is this like ionic? Is this covalent? And that will tell you sort of the rules that you have to follow. Obviously, we'll talk about it in terms of naming. So let's start with a few exceptions. And really, these first three are probably the major exceptions. There are things that no matter what they are, they typically go by common names. H2O is water. It is not a trick question. Put water on the exam and move on with your life. Don't put dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? They would like a refreshing glass of water. So it's not a trick question. H2O is water. I know I just said that, but a lot of you will miss it, I suppose, and stuff. I think I'll put it on a quiz first, and then you'll miss it on the quiz. So hopefully by the exam you won't miss it. But again, whenever you see H2O, you should always go by water. No other weird names. NH3 is actually ammonia, and you should go by that name as well, not nitrogen trihydride, which sometimes people might call it. It should be called ammonia. It also, as it might not make sense right at this moment, but it should not be confused with something else that we will see, which is ammonium and looks very similar to it, but it has a charge. So those two things sometimes get confused as well. CH4 is something we will revisit later on in the semester. That is your simplest organic molecule you could have. So when we get into those organic chapters, we'll see methane again. Honestly, NaCl, it is table salt, but most people still call it sodium chloride, and sugar, is sucrose. But I would say those three should definitely go by common name: water, ammonia, and methane. Question? Yep. Yeah, I would go with just those. Honestly, most people call NaCl sodium chloride. They don't really go by like salt, but some people still refer to it as salt. But most people go to the sodium chloride name. Oops. All right. All right, so let's talk a little bit about naming compounds. As I mentioned, there are two different types, which is our metal and non-metal, which will be ionic, and two nonmetals, which will be covalent type of bonding. Binary means there's basically two elements or atoms involved in it. When we talk about ionic compounds and we write formulas for ionic compounds, we want to always make sure that the overall charge equals 0 when we write a formula for it. For our nonmetals, there is no charge because, again, they are sharing electrons rather than transferring electrons. So it really is only the ionic compounds that will end up with things that have charges, like our cation that's positive and our anion that are negative. There really is no type of charge sort of happening in most cases in our sort of molecular compounds because, again, they're sharing electrons in that particular case. So the first thing we're going to look at are ionic compounds, which are metals and nonmetals. And really, before we look at that, we should look at this, I think. Back it up, I suppose. Let's take a look at the periodic table real quick. And when we look at the periodic table, also known as a square or box that I just drew, we have groups 1, 2, we'll go like 3, 4, 5, 6, 7, 8. And we got this kind of thing happening. I guess a little narrow there at the bottom, but you get the idea, I suppose. So we also have our staircase kind of coming down in that region, right? So when things do gain charges, and again, if you have any element that really is by itself, it hasn't combined with anything, it does not have a charge. So things on the periodic table really don't have charges. It's only they do gain charges when they kind of hook up metals and non-metals together. But when things in group 1 make a charge, they have a fixed charge of always +1. So everybody in group 1 will make a +1 charge. That's like sodium, lithium, potassium. You will never ever find like a sodium with a +2 charge because it will never happen because of what we just talked about with ionization energy. Sodium has only one valence electron, and if you get rid of that one, the next electron is a core electron, and good luck trying to take that one off. It's not going to happen. So sodium has a fixed charge, for example, of +1. We talked about magnesium, same idea in group 2. Everybody in group 2 will form a +2 charge when they do form a charge. Now, we're going to skip the transition metal region, which would be kind of in this area. And that's because transition metals can have a variable type charge. So things in the transition metals can make different types of charges. Going to group 3, which really for the most part in most cases, it's just aluminum, it will be a +3 charge. Then we kind of skip group 4, and starting with group 5, and what we're talking about here are the nonmetals in group 5. So that's the guys up to the top, kind of top right. They will make a -3 charge because they're nonmetals, right? They're going to gain some electrons. Group 6 will be a -2, also going to gain some electrons. And group 7 will be a -1. We are talking about, again, the nonmetals above the staircase, because actually below the staircase, those are metals, things like lead, tin, antimony. So again, we're just talking about negative going above. So it's kind of like 1 + 1 + 2 + 3, skip, go backwards, -3, -2, -1. Yeah. So count up to 3, count down to 3, skip 4. 4 is not really a great place because at the top you got like nonmetals, you got some metalloids, you got some metals, all in group 4. So there's real good pattern. As I mentioned before, the transition metals typically will make a variable type of charge. Like iron, for example, could do +2 in certain cases. It could do +3 in certain cases. Copper could do +1 or +2 in certain situations. But there are 3 exceptions in the transition metal region that actually do have fixed charges. And that is our friend here, zinc and cadmium. Then if you hang a left at cadmium, you'll come to silver. Zinc and cadmium, although they are transition metals, when they do make a charge, will have a fixed charge of +2. And then if you go over here to silver, kind of like a backwards L, silver will also have a fixed charge of +1. So those 3 transition metals are exceptions. They have fixed positive charges, again, of +2 and +1. Everybody else here in the transition metal region will have a variable charge, which again means in certain cases could be +2, +3, +4. And also, as I mentioned before, down in sort of this area where we have things like lead, tin, even antimony, bismuth, these guys also will have a variable charge. So in the case of like naming, those guys that are metals that are below the staircase, not part of the transition metals, but just to the right of them, will still be treated like transition metals, even though they're technically not. But in terms of naming and charges, they basically behave very similar to transition metals. So it's just that kind of backwards L here that has the fixed charges. And again, transition metals, kind of a variety of charges. Any questions on that there? Okay. So when we talk about ionic compounds, they are sometimes classified into 2 types. There's a type 1 and a type 2, and we're going to talk about what the difference is between these. But these are both ionic compounds, which means they contain, again, our metal and nonmetal. Now, let's just talk about ions in general. So if you have ions in general, that means you could have, again, a cation that's positively charged. So you could have something like H+, you could have something like Na+, you could have something like Ca2+. Any positively charged ion, when you write the formula, like I just did for all 3 of those, because they are technically ions, there needs to be charges written. So that's why the plus needs to be written, the +1 there, the +2 needs to be written. If you do not write the charge with it, it is not an ion, it's just a neutral atom, right? So it's not implied in this situation. So you do need to write the charges. If you're asked to write the formula for a cation, it should have a positive charge associated with it. How do we name just the cation by itself? If we just had that by itself, it's very simple. We just simply use the whole name of the element. So that's all you have to do is just the whole name of the element. So H is hydrogen, that would be the hydrogen, and we would put ion next to it because it does have a charge. Na is sodium, that would be the sodium ion. Ca is calcium, that would be the calcium ion. So any positive ion, which is a cation, and you have just the formula of the cation, will be named using the whole name of the element. And again, you should write the charge if you're just writing that by itself. Now, an anion, on the other hand, these are our negatively charged guys, like H minus, like O2 minus, N3 minus. The negatively charged ions, actually, we do something to its name, which is a non-metal name. So we take the non-metal name and we actually drop the last part of the name, or even a little bit more than the last part of it, and we add IDE to it. So we drop kind of the last part of the name and add IDE. So instead of hydrogen, this is what is known as the hydride ion, IDE. Instead of oxygen, we drop a little bit more than the last part. This is known as the oxide ion, IDE. And N is nitrogen. It has a charge, so this is the nitride, IDE ion. So nonmetals drop the last part or a little bit more than the last part, and we insert IDE in it for its name, and that's how we name negative ions. Once again here, if you're asked to write the formula for an anion like the oxide ion, you do have to include the -2 charge because it has an actual charge associated with it. We also see hydrogen on the positive side and the negative side. Hydrogen has unusual characteristics, that being one of them. It's the only element that will go both ways. It could go positive or negative. Everybody else chooses positive or negative, but hydrogen actually could go both ways. I would say in most cases, hydrogen will be positive. The only time that hydrogen is usually negative is if it is after a metal. So if it comes after a metal, it would be negative. So for example, if I did LiH, lithium is a metal, hydrogen is a non-metal. In this case, this is Li plus and H minus. It would be a negative in that case when it comes after it. When we write the formula for anything that is ionic, that is really made up of two charges, or two things that have charges, when we put that formula together, we need to put it together in the simplest way for it to equal 0. So when we write a formula for an ionic compound and we put our cation and anion together, we need to put it together so that the overall charge is 0. So for example, the one I just did right there, if I was going to take lithium and I was going to take hydrogen or hydride and I put these together, +1 and -1 equals 0, right? When you have that together, that means you just need one of each, and this would be the proper formula for this ionic compound. So it is kind of a weird thing for people sometimes, which is this. If you are asked to write the formula for the ion by itself, either a cation or anion, it should have charges. But when you take a cation that's positive and an anion that's negative and put it together to make an actual ionic compound between a metal and a non-metal, that formula, like I boxed there, should never have a charge. So you need to put it together so that it equals 0 in the simplest way. So for example, if I had calcium and I had bromide and I put these together, what would be the proper way to put that together? Take a moment, put it together into a formula to think what you get. You want to put it together the simplest way to. All right, so right off the bat, if I just took one of each, would the charge equal 0? No, because I have +2 and -1, right? Which if you put it together, you end up with a +1, which is not good. I need more of the positive guy or negative guy? Yeah, I just need one more, right? Like that. Now I have an overall -2 charge, right? That balances out the +2 charge, right? Now here's the simple aspect of it. I just need to count everything I just wrote there, right? So I have 1 calcium and how many BRs? 2. I put a 2. And that would be the formula. Number always goes to the guy to the left. If there is no number written, it is assumed to be 1. And that goes to the guy to the left. That's probably the easiest way to do it. Some people are taught just to switch the charges, like bring this guy down and that guy down, which is great if you're good with 93% of the time being right. Doesn't work 100% of the time, but so I would just, maybe do it the other way there so you can kind of figure it out. So this would be the proper formula for CaBr2. By the way, if I had to name that guy, what should I name it? Ca is, and Br, which is negatively charged, is bromide. So that's calcium bromide, right? So that's the name right there. Yeah. So that's all that is right there. Now, when we write the formula, as I mentioned, it does not have a charge. But you should always remember it is actually made up of things that actually do have charges. So although when we put it together to equal 0, it does not have an overall charge to the compound. It is still made up of ions. And in this case, it's made up of this ion, and that ion, by the way. What happens if I had, what happens if I had barium, which is group 2? And nitride here, and I put it together, what should the formula be? All right, so we don't put this together. We have 2 on one and 3 on the other. Common number between that is, if you multiply 2 by 3, you get 6. Yeah, so that's the common number. By the way, that would be the lowest common number, by the way. And also over here with our +2 and -1, if you multiply those together, you get 2, right? So that is the simplest way to put it together. So you don't want to overcomplicate it. I know 6 is the common number there. I just need to get each of them to 6. So how many bariums do I need to get to 6? I need how many? To get to 6? I need 3, yes? That is +2, +4, and +6. Yeah, I need 3 of them. Yeah, +6. How many nitrogens do I need to get to 6? -6, sorry. You just need 2 total, right? -3 is -6, yeah? So now my formula should be, I wrote how many bariums? 3, right? And nitrogens I wrote 2, yeah, just like that. 1, 2, 1, 2, 3. If it helps you, draw them out like that, right? It's an easier way of doing it. Any questions on that? So you could always multiply the charges in most cases together, and that will give you sort of the number that you should have probably to put them together correctly. And again, you just want to just add up all those charges until they equal those numbers. Any questions on that there? Yeah. All right, so let's talk about now really specifically here the type 1, type 2 situation here. So type 1, type 2, again, is referring to ionic compounds, which is our metals and nonmetals, which will be our ions. So these are ionic compounds. These are metals and nonmetals coming together. And again, this guy's going to be our positive ion. And this guy is going to be our negative ion in this case. So here's the deal. Whenever a metal's involved, ever in naming, it is really the most important thing. So the most important thing is always the metal. So if you happen to have a metal involved, that is definitely what you should look at in terms of how you should name it. So type 1 compounds are ones that have metals that have fixed charges. So if you remember on our periodic table we just looked at, that is everybody in group 1, group 2, group 3, zinc, silver, our cadmium. They all have fixed charges. Now, type 2 compounds are also ionic. The difference here is the metal. The metals have a variable charge. Like I talked about before, chromium, for example, could be +2 or +3 in certain situations. Copper could be +1 or +2. These are technically going to be, for the most part, your transition metals are just to the right. So again, all those transition metals, and below that staircase where you have lead, tin, antimony, those guys, those are going to be your type 2 metals. Again, it is always the metal when it's involved. That's the important thing to look at. And pretty much it will break down to one of these two things. Either it's going to be a type 1 metal or a type 2 metal. And depending on type 1 or type 2, you do slightly different things in terms of how you name them, but you always want to first determine, what type of metal you got going on. So here's a table from your book again of our just ion names, whole names here. For positive guys, IDE, again, as we talked about there for our negative guys. So let's take a look at type 1 compounds and really how you name it. So here's the deal. If you have a type 1 compound, which means you will have a metal and non-metal, we want to always look at this guy. He has a fixed charge. As soon as you identify that this guy is a type 1 metal, you pretty much could just roll right into the name. You don't have to worry about anything else. It doesn't really matter what else is there. As soon as you go, that's a type 1, all you have to do, if you're naming it, is just give the name. So how do you name it? You pretty much roll with the whole name of the metal, and then the non-metal gets the last part of the name dropped and replaced by IDE, and that is it. So, for example, we did BA3 and 2, right? BA is barium, right, which is a metal, right? And is nitrogen, which is a non-metal. That first tells me this is ionic. I'm going to look at barium, which is the metal, because it is the most important thing here. Barium is found where on the periodic table? Group number 2. Is that a fixed charge type of group? It is. It's a type 1 group, which means I'm ready to name it. So the whole name of BA is barium, and nitrogen becomes nitride. There it is. Yeah. Now you may be saying, hey, what about the 2? What about the 3? I should lay up me some prefixes like a di or a tri. And I would say to you, you should not lay up a prefix unless you would like an X. Yes, because it will be wrong. People always want to use prefixes where they shouldn't. And there are special places where you should use prefixes. And let me tell you that typically speaking, if there's a metal involved, there should be no prefixes ever. Yeah. So people always want to throw at the end there dinitride because it sounds more chemistry-ish, but it's not. It's just wrong. So don't use a prefix in this situation. The 3 and the 2 is there because this guy's actually made up, as we saw on the previous page, of ions, right? It's made up of barium ion. It's made up not of one of those guys, but it's made up of 3 of them, right? So that's what the 3 represents. The 2 represents that there are 2 of these nitride ions. By the way, when I wrote the formula here for my anion, did I put the 2 on the bottom? Did not, because that doesn't exist. Yeah, so the 2 means that there's just 2 of those ions. You should not put the 2 there. By the way, you shouldn't put the 3 there either, because that doesn't exist either. So don't do that. Again, those numbers represent how much of those individual ions you have basically there. So if you're asked to write the formula of the cation, so if you're asked to write the cation formula, you should just write that, what I just circled. That would be the correct formula for the cation. And if you're asked to write the formula for the anion, that would be the correct formula. You don't incorporate the little subscripts into the ion guys. And again, that would be the name. We did like this guy earlier, right? What should this one be called? This is calcium bromide, again, because calcium is group number 2, type 1. Br is bromine, which is a nonmetal. That's a type 1 compound. Calcium whole name. IDE for the second. Calcium bromide in this case. Right? By the way, I did this one earlier. That would be called So you got half of it right. That's lithium, which is a metal, right? And hydrogen, which is actually a non-metal, right? So this is a coming second. So our cation here again is the +1. Anion is the negative, which means this is lithium hydride, IDE, the negative version of hydrogen in this case. Yeah. Any questions on that? So type 1, pretty much whole name. And then you just roll with the IDE at the back end of it. So remember again that when we write formulas, also for ionic compounds, so when we write ionic compound formulas, it is always the cation first, which is the positive guy, followed by the anion. That goes for when you write the formula. It also goes for when you name it. You always go positive to negative, always when you're naming anything that's ionic. So both when you write the formula and when you name it. So that's why when we look at Ki here, again, we could dissect it. K is a metal. I is iodine, which is a non-metal. By the way, that combination right there, those two things automatically tells you you're in the ionic compound region. We also have a metal, which, as I mentioned before, is always the most important thing. And potassium is group number 1 on the periodic table. If you look at it there, that means that it has a fixed charge of +1 and also means that it's a type 1 compound, which means we would roll right to the name, whole name of the metal, which is potassium. Iodine, we drop the last part and put IDE at the end of it, and it becomes potassium iodide in this case. Now that potassium iodide, the way the compounds formula is written, has no charge, which is correct. The formula for the cation in this case is a potassium with a +1 charge because it's group number 1. And the anion is I with a -1 charge because it's group 7 on the periodic table. When we put that together, +1 and -1, we just need one of each, right? So that's how we get to that formula there. So once again, the formula for the ionic compound has no charge, but it actually is made up of some things that do have charges. So it's kind of a concept sometimes people have trouble with because they're like, should I put the charge on that or not on that? So once again, if you're putting the metal and non-metal together to make the ionic compound formula, no charge needs to equal 0. If you're asked just to simply write the formula for just the positive guy or the cation, you need to include the charge. If you're asked to write the formula for the negative guy or anion by itself, you need to include the charge. So if you're asked to write a formula for anything that has a charge, you need to actually write the charge in. But when those two guys come together, no charge needs to equal 0. In the simplest way, by the way, to equal 0. There's lots of ways to equal 0, but the simplest way that you could get it to balance out to 0. Any questions on that there? All right, well then, why don't you try some here? I think we actually did that. So let's change this one. Let's do MgCl2. Why don't you also write the formula for these things? Let's do let's do sodium oxide. Let's do aluminum sulfide. And let's do potassium. Let's do potassium phosphide. All right, so on the left-hand side, proper names, right-hand side, proper formulas. Okay, so since we're getting in, let's take a look at these here and see. So again, really the first thing you might want to do is identify what you're dealing with. So K is a metal and Cl is a non-metal, which is chlorine. So that combination should automatically tell you that you are in the ionic sort of genre here. Once we have a metal involved, that again is the most important thing to look at. In this case, that is potassium, which is group number 1, which tells us it's a type 1 metal because it has a fixed charge. And that's really all we have to look at that point. Once we determine that, we could just go the whole name of the metal, which would be potassium. And the chlorine now will become chloride, right? And IDE at the end of it. This is made up of two ions. Potassium, that's +1 because it's group number 1. That's the cation, right? And the anion here would be group 7, which means it has -1 charge, which is Cl, and that would be our anion. That is also why when we look at the formula, it's +1, -1. We just need one of each to get it to 0, and that's why the correct formula is KCl. Question on that one there. Looking at the next one, we have Mg, which is a metal. Cl, which is chlorine, which is a nonmetal. Again, that tells us it's ionic. We're going to look at the metal, which is magnesium. That tells us it's group 2, has a fixed charge. That's a type 1. In terms of naming, that's all we need to know at this point. We're going to use the whole name here of the metal, which would be magnesium, right? And the Cl here will get the IDE treatment and become chloride. Do I put a di in front of that? No prefix, right? So again, the cation in this case is going to be magnesium with a +2 charge, right? The anion formula is Cl minus, not Cl2 minus. It's just Cl minus. That's group 7. That is the actual ion, right? The 2's there because we don't need one of them, but we actually need 2 of them, right? So that's why the 2 is there to balance out the charge, okay? So again, when you go to write the formula, if you were asked to do so for the anion, it should just be 1 Cl with a -1 charge because it's group 7. Question on that one there. Coming down here, we got barium, which is a metal, hydrogen, which is a non-metal. Again, that's ionic, and we have type 1 because barium is group number 2, has a fixed positive charge of 2. So we will roll with the whole name here of barium. And at this point, we've seen it a number of times. The hydrogen in the negative version is hydride, IgE. This is made up of a barium cation with a +2 charge and 2 of these hydride anions, right? -1 each. Again, -1, -1 is -2. That covers the +2. Any question on any of those names there? It will. The non-metal, for the most part, in pretty much all naming, except for one area, will pretty much end up with ID at the end of it. Yeah. And again, as you can see, as you will see, you sometimes drop a little bit more than the end of the last part of the name. So some drop a little bit more and stuff, but it definitely will always end with the IDE for the non-metal. All right, now we want to write formulas. So basically, we just do the opposite, right? We know we want to figure out what it is. So sodium is group number 1, right? Which means it has what's of charge? +1, right? Oxide is oxygen, which is group number 6 on the periodic table, has a -2. We're now putting a metal and non-metal together, things with charges, which means it needs to equal 0. I need more of which one? Yeah, I need one more, right? That gives me a +1, +2 to balance out the -2. Now I can just count what I did, right? I got 1, 2 of those, so an Na with a 2, and I only have one of those. There it is. Yeah, I'll just put it together and you're all done. Yeah. Question on that one there. Next is aluminum, which is group number 3. I'll go down here. That means it has a +3 charge, right? Sulfide is sulfur on the periodic table. That's group number 6. Has a -2 charge. Common number when I put that together is 6. 3 times 2 is 6. So to get aluminum to a +6 charge, I need a total of 2 of them. So I need one more, right? And to get my sulfide to 6, I need a total of 3 of them, right? +3 is +6. 1 plus -2 -4 -6. That will equal 0, correct? So all I have to do is just write what I did. I did 2 aluminums, so an Al with a 2 next to it, and I did 3 sulfurs. There it is, yes. Any questions on that one there? Lastly, I got potassium, which is group number 1, has a +1 charge. Phosphide is group number 5, which means it has a -3. When I put this together, I need more of which one? I need a grand total of 3 of them. So +3 balances out the -3. I have 1, 2, 3 Ks and only 1 P, right? There it is. Yeah. So if it helps you to write it out like that, do that. Yeah, why not? What do you care? And put it together and just count what you wrote, right? It's just kind of a simple way to do it, I suppose. Any questions on that? That is type 1. That is a sampling of nomenclature.